We're getting started Santa Fe time. So thank you very much actually for being here. This is honored to be up on the stage right now and actually kick off the professional part of the summit. As most of you know, it's a lot of work to put together a schedule like this. Started over 6 months ago with a plan, and then the plan has actually come together. As most of you know, we have actually speakers from around the entire Southwest you're going to see today, and they're going to participate in the workshops. That was the plan that we started with 6 months ago, 7 months ago. Pretty unbelievable that it's actually come together. And what is actually even more unbelievable, the caliber of speakers we have. This is our second event. It's going to be hard to top it with a third event, but I'm getting lots of ideas from you on what we can do next year. But part of the idea was actually to talk about our water supply, where it comes from, have people from all the southwestern states here to really work, and that's what the point of the shreds are tomorrow, to work on some possible solutions. Then when you start, okay, that's what we're going to do, what do you do for your keynote? It's like, okay, so now you've got to find somebody that's really specialized in an area that's, big, Colorado River, and actually covers 7 states, and as Kim likes to mention, 5 states in Mexico. But somebody that really understands what's happening with the Colorado River Basin. And in looking at that, it was amazing. Made a couple phone calls, and very, very fortunate to find the speaker that we have this morning, who used to be at Tucson, who has ties to the Santa Fe community, which was just, you're sitting there going, okay, what are the odds of this? Finding somebody that actually is, from Arizona, one of the states we're talking about, actually has ties in the Santa Fe area, and actually knows something about the subject we're going to talk about. In fact, not just knows something about it, is one of the foremost experts on it. And it is really, really my privilege to kick off this morning and introduce Jonathan Overbeck, and he goes by Peck. That was something I had to get used to, I have to admit. Calling a dean of the University of Michigan Peck was just like I had to wrap my brain around it. But if you call him Jonathan, he may not pay attention, but if you call him Peck, he turns around. So it's like him, sort of just as an individual, that's what he does. And he's got a huge program. University of Michigan is a brand new program, it's a combination of lots of schools up there. And he is the guy you're going to listen to. And this morning, I'm really, really honored to introduce him and kick off the summit with Peck. Thank you very much for being here this morning.
Good morning, everybody. It is great to be back in Santa Fe. It's where my folks are from. And I still have a place up in the Rockies in southern Colorado, so I spend a lot of time out here, but any chance I get, I'm eager to come out and talk about what I spend a lot of time, my own personal time, research time, and time engaging with stakeholders, whether they're communities or water managers, ranchers, foresters, just about anybody, to talk about what's going on in the Southwest, what's going on in the West, and what can we do about it. So I'm pleased to be able to talk about that today. I'm going to do a couple things in this presentation. Doug wanted me to talk about the Colorado, and that's something I've spent quite a bit of time on. I have some recent scientific publications that are, I think, very important to communicate beyond the scientific colleagues, and I'll talk about that. Put a little context of some of the other things you're seeing. I mean, if you look at any of our weather reports these days out here, unfortunately you don't see a snowstorm pending. What you see instead is red flag warnings because it's so darn hot and dry, and the wildfire risk is exceptional. And of course there's a nice size fire going on right now in New Mexico, and it's just the start of what's likely to be a pretty horrendous fire season. And then I'm going to talk in Act 2 about drought and mega drought. This is mega drought country that we're living in, meaning drought that lasts more than 20 years. And anybody who's gone up in the Four Corners and listened to some of the traditions of our Puebloan neighbors, you know that drought has factored in for millennia in this part of the world. And then at the end, I'll talk about whether there is any good news in this story. It's a rather depressing story, but I think in the end, there is good news. And it means, of course, like most good news, it means we have to do more work, but at least it's not all bad. All right, this first part is really looking at Southwest North America and the Colorado River. And the best place to start in all my presentations is to look at the current state of the drought. The drought. This is a drought that's been going on since 1999. Some of my colleagues in Arizona said, well, 1998 is when it started in Arizona. I don't like to quibble, but it's been going on for nearly 20 years, and I've been asked all along, is this a megadrought? Is this a megadrought? We coined that term a couple decades ago as something lasting more than 20 years, so gosh, we're getting awfully close. And you can see where the drought is now. The darker the colors, the more tough it is. We've got exceptional drought here in New Mexico. All of New Mexico is in drought. The last time all of New Mexico was in drought, Senator Bingaman had me testify before one of his committees, and well, here we are again. You know, this drought's been moving around, and you can see that in this, just looking at 4 other years. It started in 99, but really the watershed year, the first watershed year was 2002. And I'll show a picture of this later on, but those of you who spend time in northern New Mexico know that's when a lot of our pinon pine just often died initially just because of the heat and drought. And of course then the insects came in and made it a lot worse, and a lot of the other species of trees in the Southwest are getting it now. But the drought has moved around, and sometimes it's looked like in 2012, it's looked like the Dust Bowl. It's out there on the high plains, but most of the time it's back tucked in here in the Southwest. The California drought is part of this drought as well. And New Mexico and Arizona tend to be the ones that get it more often than not. Well, the focus of this talk, if it has any real special focus, is on the Colorado. And as Doug mentioned, a number of states, 7 states share this water, all the way up to Wyoming and down here in New Mexico and Arizona over in California. And you can see on this map, let's see how well it projects, a couple things. One is I made Santa Fe a nice big dot, just so you know where you are. Santa Fe, of course, cares about the Colorado because there's a San Juan Chama diversion of water from the Colorado basin into the Rio Grande. But the story I'm telling today is about the Colorado, and of course that means it has something to do with your water here. Every glass of water you drink here has some Colorado River water in it. But this is the same story for the Pecos or the Rio Grande or a host of other rivers in the Southwest. It just turns out the Colorado is the most iconic and important river in our region, and that's why I'm highlighting that. That's where the scientists have focused most of their work. But the story is very similar for the Rio Grande, only worse. 7 states, it's a fast-growing part of the country. We're over-allocated even before we factor in what I'm showing you today by about 15%, 10-15%. Huge agricultural production. Even the romaine lettuce is usually edible. But all of our winter vegetables, that was a bad joke, all our winter vegetables in this country, of course we're importing some, but all the domestic ones are coming from Yuma and the Imperial Valley down there near the mouth of the Colorado. Huge amount of native nations in this region, many of whom still haven't had their full water rights adjudicated. So in other words, they are owed and will get a significant amount of the water that flows in the Colorado that's not yet allocated to them officially. And if you're in Arizona, it's really your only sustainable water supply. Everything else is really fossil. And there are a few streams flowing off the Salton Verde. They flow into Phoenix, for example. But those streams are going to undergo just a whole pile of hurt even before the Colorado, and they already are. I'm not talking about things that are going to happen. I'm talking about things that are happening, observable. And I'll talk a little more about that because that gives us a lot more scientific confidence. Okay, everyone in the room who's in this neck of the woods knows that it's been a horrible snow year in the southwest headwaters of the Rio Grande and the Colorado. Most places, the snow water content, we can measure the depth of the snow, but what's really important is how much water is in that snow. Most of the Colorado watershed, the water content right now is 25% or less than normal. And in some places it's as much as half normal. And down here in New Mexico and Arizona, it's below 25% of normal, so it's bad. Lake Powell and Mead are the two biggest reservoirs in the country. Lake Powell's right at the junction between the upper basin of the Colorado and the lower basin. The lower basin is Arizona, Nevada, and California, and the upper basin are the other 4 basin states that share the water with Mexico. Lake Powell is 52% of normal, and Mead is 40% of normal. This isn't as bad as it's been, but with this really low snowpack this year, we're likely to see these reservoirs go below where they've been in this drought and be very close to an official shortage, which is declared first when Lake Powell hits 1075 feet above sea level. We're about 1080 now. But with this horrible snowpack, it's going to be darn close. And that's why you see people starting to fight about the water, the upper basin and lower basin. Okay. Let's look at some science and what's been happening here. And this is all based on observations. None of this is that fancy. It's just measured change. Okay. What we have here, I like to face this slide. On the top is we have the combined storage of Lake Powell and Mead. And one of the beautiful things about this, our forefathers who envisioned these reservoirs did a really amazing job, because most people in the Southwest haven't really felt the drought in terms of water shortage or anything. And that's because of this amazing water infrastructure. But we're getting to the point now where it might break. But you can see we built in the Depression years, we built Boulder Dam, then known as Hoover Dam, filled up Lake Mead, and then we got into the 50s, and through the 60s, we had a drought. So that lake, that reservoir, didn't fill anymore, and there weren't a lot of people out here in those days, so it wasn't a big deal. But everybody's, was thinking, wow, we want a lot more people to move to the Southwest. We better get more water storage. So that's when they built the Glen Canyon Dam and started filling up Lake Powell. And you can see the combined storage peaked in the 1980s. There was a small drought in the late 80s. And then we filled up again. I moved to Tucson in 1999 when the reservoirs were just brimming full. And I still love to tell the story of how I went to Nevada, the Southern Nevada Water Authority, probably the most sophisticated water managers in the Southwest. And I said, you guys have to worry about drought. And they literally were laughing at me. And then immediately upon leaving the room, it seemed the drought began. And I only wish I had been wrong. But we hit those really dry years in the early part of this century. And then we were able, with a bunch of good years, interspersed with the bad years, to sort of keep things full. And now we're back into sort of this bad, potentially very bad situation. Because these reservoirs are all in river valleys, if we start going down below a certain amount, it will start to go much lower fast. So what is behind these changes that we've seen in the Colorado? What we see here, to start, is the naturalized flow. And what I mean by that is water managers, we have a lot of other reservoirs on this river. We can account for all those reservoirs and calculate what would the flow be in the river if we didn't have the reservoirs. That's a pretty easy thing to do. And you can see on this graph and the next graph, 3 colors. You see the white line going up and down. Those are the year-to-year flows. in this case. The blue line is put in there to be sort of show you the low frequency or the slowly changing pattern. So you can see during the 50s and 60s drought, the flow went down on average, substantially, then came back up. And now in our current drought, it's gone down again. And then the dashed red line is the long-term trend. I just put a straight line through that best fit line. And you can see that over the period since we started taking measurements back in the early part of the 20th century to today, there's just been a steady decline in the flow of this river. Okay, and one of the interesting things is the flows in the 20s were pretty much as high as they've been in the last 1,000 years. Now we know that from tree rings, and that's when we divided up the river water. Okay, so now those two graphs are on the top of this plot. So there's that combined flow up there. There's the long-term naturalized flow there, just going down. Excuse me. Why is it going down? Well, here we have precipitation. Your first thought when you say drought, oh, that means less precipitation. And that is the way even my climate scientist colleagues usually think about drought. But that's changing fast. Okay, because if you look at precipitation in this region, you can see the ups and downs. And if you have a good eye, you can see the blue line goes down during the 1950s and 60s drought, meaning that drought of low flows during the 50s and 60s was due to lower precipitation. Okay? That's why we always thought of the 1950s drought as a precipitation drought. But then look at the current drought. Precipitation has only been, if anything, a little below normal, about normal. So precipitation isn't the cause of this drought. It is a contributor, but it's a sort of secondary contributor. The main cause of this drought is temperature. So look at temperature here, and you can see, and also well, look at precipitation. The dashed red line has been perfectly flat. In other words, no trend in precipitation. There hasn't been an increase or a decrease over the last 120 years. But if you look at temperature, in contrast, that red dashed line is going up. And it's a mirror image of the flows here going down. Okay? So the 50s drought had normal temperatures below normal precipitation. That was the drought, a precipitation drought. This drought, in contrast, about normal precipitation, but way above average temperature. So this is a temperature drought. Fundamentally different kind of drought. This is the kind of drought we're going to have to deal with in the future. But as you'll see in a minute, they might coincide with a precipitation drought as well. Why are the temperatures going up? Well, here's a map showing a global temperatures trend from 1901 to 2012. Anything that's orange to red to purple around the globe is where you have temperatures going up, measured by thermometers, measured by satellites in the recent part of the record. This is like known with great confidence that everywhere around the planet, except a couple places, such as in the North Atlantic, and just recently we got another jump in temperature of about 1/4 degree C. This cold anomaly has gone away. Everywhere on the planet now is warming except the North Atlantic. And that's again why we call it global warming. Okay. We don't have data down here in the Antarctic or up in the Arctic because we didn't have thermometers back in those regions in sufficient density to calculate this in 1901. But we know now that these regions, both of them, are warming dramatically, especially the Arctic. So the whole planet is warming. And what we're seeing in the Southwest is a local manifestation of that warming and the effect of that warming on our river. So how is atmospheric river knocking back the flows in our river? How is the atmosphere knocking back the flows in our river? Okay, and in other words, how is it essentially vaporizing our water? Where is the Colorado River water going as the temperatures go up? And the first clue you have to realize is that as the atmosphere warms, it can hold more moisture. Okay? This is something that was predicted, probably 150 years ago, and we are observing it. We can measure the water content of the atmosphere go up, and it's going up just as we predicted. Okay? That means the atmosphere needs more water and more water as it warms and warms. Where's it going to get that water? Anyone who gardens knows one place it'll get that water, right? Your plants wilt when it gets too hot in the summer, and you have to water it more. Because the plants are actually taking the water, they're photosynthesizing, they're sending the water back into the atmosphere through their little openings in their leaves called stomata. That's called evapotranspiration. And that turns out to be the very biggest cause of the temperature-induced drying of the upper basin of the Colorado, or for basically the planet, okay? But also what's happening, for example, this year in the upper basin, spring has come two weeks early. On average, it's coming even earlier than that now. So the plants are greening up, they're using water much earlier. So again, they're taking water out of the soil, and that was snow, and they're transforming it into vapor that goes into the atmosphere. You also have sublimation from snow. So sometimes as it warms, a lot of the snowpack is actually going directly from solid form of water, snow, into a vapor form of water. And that is a process that accelerates with warming. Everybody knows about evaporation. It's hotter, you get more evaporation. That's going on. And you get these other changes too, which I'm not going to go into detail, but more rain is not good for the flows, and we're getting a lot more rain now than snow because it's so warm. And the rain, when it hits the snowpack, also destroys the snowpack. So all these together, plus some positive feedbacks, meaning amplifying factors, which I'm not going to talk about, all of these are resulting in the flows of the Colorado going down and down as the atmosphere warms more and more. I wrote about this in 2013 in a paper in a prominent scientific journal, just to say to my colleagues, stop thinking about drought as precipitation, because in the future, drought is going to be driven more by temperature, more and more as it gets warmer and warmer. And this is a whole new type of phenomenon. And now, several years later, pretty much, there are hundreds of papers written about this. And I'm not taking credit for it, I'm just saying my community, we all are starting to realize this is a serious problem. Here's that picture I promised you of the pinon and pine, juniper woodland, up in just northwest of here, taken by Craig Allen, a New Mexican, works for the U.S. Geological Survey. You can see the juniper trees were unaffected in 2002, 2003 by the drought, but all these gray trees, those are all dead pinon pines. Fortunately, there's still piñons in some places, right? We know that. But in this neck of the woods, they got hammered. And this is exactly where this year's drought is hitting the hardest, same place. So it's going to be interesting to see what happens to the trees there. Remember the California drought? 5 years of really unusual drought. Also a very hot drought. And it's leading to widespread tree death in the Sierra Nevada, and that's just starting to play out. The trees don't always die immediately, it takes them a couple years. They're tough, but not tough enough. Along with the tree death, along with the insect outbreaks that come with warming and drying, because the trees aren't able to produce the sap they need to fight off the insects, and also the insects are able to have more life cycles as it warms. You're getting a lot more dead vegetation, but you're also getting a lot more wildfire. This is just to highlight one of the biggest fires ever in Arizona. Of course, up in the Jemez near here, just west of here, we've had just this whole series of just huge fires, including ones that have threatened the Los Alamos National Laboratory. And you don't want to threaten that laboratory. It's got a lot of radioactive things still in the soil and everywhere. All right, and if you look at a map just showing, this was produced by one of my colleagues at the University of Arizona. These are the forests of the West, and you can see in green, this is out of date now, right? This is up to 2011. So a lot of these green forests have now burned, but as of 2011, all the brown are the forests that have had significant fires. That doesn't mean we've lost the forest, it just means they've burned. And you know how fires are. Sometimes they're like a devastating burn. You don't see anything except charred sticks sticking out of the ground. In other cases, you have patches of burned and non-burned. But I'm just using this to highlight that wildfire is going crazy in the Southwest, and it's for the same reason. Okay, that's all the stuff that's happening. Now I want to talk about what's going to happen, because everybody needs to know, well, the flows are down. You know how much the flows are down in the Colorado over this drought? 19%. We think about half of that is due to temperature at least. I personally think more, but science-wise, we can pretty much convince our colleagues at least half is due to temperature increase. So 10% due to the temperature already. Okay. Up until recently, there have been lots of papers written about the Colorado and how much flow we'll lose by mid-century. And the good news was there was consensus among the scientists that all the studies that were done said we're going to have less flow. This is before the drought really kicked in. Some said, oh, it'll only be a 1% down by mid-century. Others said as much as 45% down by mid-century. So we set out with a whole group of colleagues, many of whom wrote these papers. We want to get a better number. We want to figure out why our estimates are different, use common assumptions, and figure out a better, best estimate of what's going to happen to the flow. And I'm going to show you that today. But first, I want to talk about what's ahead in terms of temperature. Okay. Turns out these are two maps. One on the left shows what happens if essentially we agree and we are successful at meeting the Paris Agreement Accords. In this neck of the woods, that means we get another degree and a degree half warming. Think of that as the best case scenario. If we continue to burn fossil fuels at the rate we've been burning over the last couple of decades, business as usual, this is the Scott Pruitt version of the future. I don't want to make this political, but that's essentially what he's trying to push. Then we're going to warm 5 to 7 degrees more. What's important to realize is people often say, well, global warming is only going to be 4 degrees in the business as usual case. Those are degrees C, which is 1.8 degree F. And the other thing to realize, just like in the observations of the warming so far, the projections all show more warming over land and at higher latitudes. Well, we're over land and we're at higher latitudes. That's why our numbers are bigger than the global average. Whatever the global average is going to be, we're going to be warmer. All right? The biggest uncertainty when trying to predict, we call it project, future temperature, isn't our climate models. Our climate models are well tested against past observations, both of the last 150 years, but thermometer and rain gauge and such, but also paleoclimate measurements, trying to simulate the climates of the glacial period, the time of the dinosaurs, things like that. We can do that. The biggest uncertainty turns out to be how much greenhouse gas we're going to put in the atmosphere. The biggest uncertainty is what are humans going to do? You know, we agreed as nearly as 2 years ago to really make a lot of emissions. All the countries in the world agreed to do this. Now, the most important country of the world in terms of emissions has said we're not going to try and do this. But of course, then some states like California and Northeast, they're still going to do this. So there's a lot of uncertainty what's going to happen to the emissions. But this is kind of the range I want you to think about as I talk about how that's going to affect the flows of the Colorado and the Rio Grande. Next, I want to just take a side to say what gives us confidence in these climate change predictions. You know, usually scientists get up and they just say, well, this is the way it is, I'm a scientist. Okay? That's kind of unsatisfying to me. It's probably more unsatisfying to you because there's a lot of uncertainty in doing this work. But I want to tell you how I gauge uncertainty. Okay? The first thing I look at is if our forecasts or our projections of change are consistent with experimental evidence. In other words, you can do experiments where you put CO2 in a chamber and watch how that will affect the water holding capacity of the air. You can also put radiation on that increased CO2 atmosphere and see how it changes climate. You can actually do this with physics without even having to do any experiment. You can just base it on math and physics. Okay? If you put more CO2 in the atmosphere simply has to warm. Okay? That's not always enough for some people. The question is it consistent with observations? We've put a lot of CO2 in the atmosphere. We've done a big natural experiment. What's happened to the global atmosphere? So far it's warmed a degree C. A little over a degree C now. Okay? So it's consistent with the basic physics and with the experiments. Okay? Now we have these climate models which essentially represent our very best understanding of all the complexities in the climate system, because there's a lot of feedbacks, clouds, and the effect of volcanoes, and the sun's radiation changes by a little bit. I want to see consistency among the models too before I put a lot of confidence in something's going to happen. Why am I showing this to you? Because future warming, I'm going to say right here, and I've said it before, is a sure bet. There isn't a bet you could make that is more guaranteed to come true. You could you could bet your house, you could bet your car, if you could get this kind of bet in Vegas, we'd all be rich. Okay? Because it's consistent with the theory, it's consistent with the experiments, it's consistent with what's happening, Mother Nature, and all the models agree that it is going to warm if we continue to put CO2 in the atmosphere. There's just no doubt about it. And that is very important for us, because if we want to have management strategies, and we want to employ those management strategies, or we're going to decide we're going to put big money into water-saving strategies in our home developments, for example. That's a big investment. Are people going to pay more for that? You want to be darn sure that they're going to need that. And you can be darn sure. Okay? This is just showing a range of the models, 39 of them, the state-of-the-art models that were used in the Intergovernmental Panel on Climate Change, showing the coldest projections from the coldest 25% to the warmest 25%, and the ones in the middle. The important thing to realize is every model is saying this region is going to warm. But it could warm 4 to 5 degrees C, or it could warm 5 to 7 degrees. Okay? Depending on which model, because some models are warmer than the others. You know where most of the heat goes with global warming? It goes into the ocean. Over 90% of the heat is being absorbed by the ocean. Some models put more heat into the ocean, some less. Depends on how they simulate ocean circulation. That's where you get this range. So we took those numbers, and I'm going to show you the results in just a second. But first we had this paper, which is on the cover of one of the top journals, trying to reconcile all of those simulations or those projections of flow. What is this warming going to do to flow? We came up with this estimate. We're going to get declines in the Colorado River of 6.5%, plus or minus 3.5%, for every degree C warming. Okay, we've had about a degree and a little over a degree and a half already. We've lost 10% of the river so far. Okay, that range is one standard deviation, so somewhere between 3 and 10% of flow per degree C warming is our best estimate. And this paper had all the old all-stars of Colorado River stream flow projection, and some people like me too. Then in another paper, Brad Udall, this is the cousin of Tom Udall, who's talking tomorrow. He's a water resource manager and scientist. He and I have worked together for quite some time. We had another paper come out in Water Resources Research, the top hydrologic journal in the country, where we took those numbers, estimates, and we connected them with the climate model projections to get an estimate of what's the likely flow reductions. And you've already done the math, I hope. Okay, but if you take into account that we've already had 10%, so we're probably in the upper end of that range of sensitivity I just showed you. This means if we do business as usual, this river is going to be knocked back at least 50% of the flow by the end of the century. Some of the models say, 70 or 80% of the flows will be reduced. Will be gone. Right? That's the cost of global warming for the Southwest. Everyone says, well, what's the big deal about a little global warming? This is what happens to the Southwest. Don't forget the tree mortality. Don't forget the wildfires. Don't forget, if you're in Arizona, the dust storms. All those things are starting to really tick up. It's all related to the same thing, warming and drying. Some of you, if you've followed the literature, would say, what's the big deal? Some of my colleagues say that. We have some climate models that say it's going to get a lot wetter in the Southwest. Well, that's why I showed you how I decide as a scientist what I put my faith in. Because Mother Nature is not showing any increase in precipitation. Precipitation, I've showed you the data, it's been flat across the upper basin. Hasn't gone up at all. So what do you think about those climate models that say it should be going up? Maybe there's a problem with them. Well, we're digging into that, we're starting to find problems with those models. Okay? It's not something you want to bet on. Okay? Don't bet on precipitation. We're not getting an increase in precipitation. Why would you say all of a sudden those models are right? We're going to get it. And some models say no, a decrease in precipitation. Some say no. Most models say no increase. But more importantly than this, and this is something Brad and I put in our paper that I think is really important for water management or anyone else who cares about water in the West, it might not even matter what average annual precipitation does. It might just not matter. Maybe it will go up. And I'll give some of my colleagues, scientific colleagues, credit for convincing me that there are ways that could start to happen. But even if it happens, why do I think it doesn't matter? That brings us to the next act of this story. We're going to talk about drought and megadrought. Okay? They could overwhelm any average increase in precipitation. So what? Precipitation starts to go up a little, and then we get a drought. What does that do? It means we get below normal precipitation for 5 years, 10 years, 20 years. How long can we possibly go without any precipitation? Well, the tree ring record extends back now multiple millennia in the Southwest, and we can get an estimate of how many droughts have we had, how long did they last, things like that. The longest drought in the Colorado and Rio Grande headwaters, just north of here. This is one of my grad students who did this work with tree ring work. Connie Woodhouse is the goddess of dendrohydrology in this region, and she's at the University of Arizona. 50-year-long drought. This is about 200 AD when this happened, with 1 year above average precipitation. During medieval times, the times when people moved out of the Four Corners and moved here along the Rio Grande and down to Hopi and down into Mexico, those droughts lasted 25, 30 years. But the longest drought we've seen is 50 years. These droughts happen. Okay? Another grad student, Toby Ault, worked with Julie Cole, another professor at Arizona, and I, to get an estimate of how does the warming change the odds of a megadrought. The warming increases the odds of megadrought in a non-insignificant manner. The odds of a megadrought less than 25 years, 17%. Think about that as we're in the 19th year of the current drought. Odds of a 50-year-long drought happening in the second half of this century, almost 10%. So even if precipitation starts to go up a bit, we get one of these droughts, bang, we're back below normal precipitation, and we still have the full effect of the temperature-induced drying. So if you really are planning for the future, and a lot of you are involved in projects, therefore they're going to be here for a while, right? This is what you have to plan for if you assume global warming continues. Obviously, if global warming is slowed and stopped, then we don't have to worry about these big numbers. But we still have to worry about some further declines. But just due to the warming, we could get 50 or more % reduction in flows. And the Rio Grande is worse. I'm guessing. No one's done the full study yet, but we are seeing the temperature-driven reductions in the Rio Grande now. Okay? And then during these mega droughts, at least 15% reduction is what we've seen during the previous mega droughts. There's a lot of debate whether it was more than that or not, but this is a conservative number. At least 15%. And that could be for years, decades. Okay? Now, I just want to show you this because we're not alone in this world. You've heard about what's going on in Cape Town. Some of you heard about the drought that was implicated in the beginning of the Syrian mess. It was obviously much more than that. But some colleagues think the drought played a big role because it was the worst drought Syria's ever had in the instrumental record. But if you look around the world, this mega drought problem is something that we're not alone. There are a lot of places, and the red show you the drought-prone regions of the world based on the climate models, and then the numbers are the longest mega droughts we've seen in recent paleoclimate history. And in the Amazon mega drought, the longest drought we've seen in the record of rain gauges is 1 year. So people think 1 year is a horrible drought. Well, we now know the droughts can last 10, 15 years in the Amazon. Australia is sort of like here. You can get droughts that last, pushing a century. In the headwaters of the Colorado, the longest drought we've seen is 50 years, but over in California, we've seen one that lasts 100 years. Okay. The Sahel drought of the 1970s, 80s, 90s, that's sort of the first and only observed megadrought that we've seen in the rain gauge record. But we go back just a little bit further in time and we see droughts lasting more than 100 years. Okay. Monsoon Asia, the droughts don't last as long there, we've discovered. But the point is these are all places in the world where if they're not careful, they're going to get hit hard by the temperature-induced drying coincident with a drought. Meaning even if they're going to get more precipitation in a warmed world, they'll have periods where that increased precipitation fails. And during those periods that can last decades, they'll get the full effect of the temperature-induced drying. Now there's one other part of this story that's very important to us in New Mexico and Arizona in particular, but I think also the high plains. We all fly over the high plains. The high plains has one of the most amazing aquifers. Arizona has one of the most amazing groundwater reservoirs. New Mexico, not so much. In Arizona, though, we're getting these fractures, what do they call it? Earth fissures. There's over 200 miles of these things now. What's happening is, mainly because of the farming, but also you're seeing this in the cities, as we pump the groundwater out, the land subsides, and these things go all the way down to the water table in some cases. They fill in with dirt and everything, but when they occur, this is because we're draining our groundwater. And our groundwater in many places, not all, but in many places, is fossil groundwater. It was water that accumulated over millions of years, predominantly when there was a colder, wetter climate in the Southwest. So we pump that water out, it is gone, just like we pump oil out of the reservoir, and eventually it's gone. And this is just a recent map showing where we're getting a lot of irrigation. Obviously up in Colorado, they're irrigating with water that probably recharges. But down in our neck of the woods, the water isn't going to recharge. We pump that groundwater out. It's much harder to get it back in, unless you're right along the river, of course. But then you're basically, if you pump the groundwater next to the Rio Grande, what happens? The Rio Grande goes down because they're connected. Right? And out in the high plains, I'm really starting to worry about that. Because that is clearly the Ogallala aquifer is drying up. And it's there for another 50 years maybe, maybe not. But when it's gone, it's gone. And there's no such thing as rain-fed ag out there anymore. So, big question for us all to think about. We just wrote a policy piece about this. Because, we've been spending the last 10 years, 20 years talking about megadrought, and then this might be our first megadrought. And just as it turns 20 years, and the journalist asked me, well, Overpeck, you've been saying it had to last 20 years to be a megadrought. It's 20 years now, so is this a megadrought? Am I going to say yeah? I'm going to say maybe. Because I think something else might be going on, okay? this might not be a megadrought. This might just be the aridification of the Southwest. And so many of our colleagues, both in science and out, think, oh, we just have to wait this sucker out. But we might not be able to wait it out, because it might just be getting drier and drier and drier as long as we keep warming the darn planet. And that to me is a pretty scary thought. Now, what drives megadrought also drives, it's really low frequency climate variability, and we don't have to get into the nuts and bolts of that. But that means that we are going to have, just as we get long periods of below normal precipitation, megadrought, we get long periods of above normal precipitation. We call that megapluvial. And we haven't studied them as much, but they do happen. And that means that we will get periods that could last decades that have more precipitation than normal. But of course, that'll be fighting against the warming effect of the temperatures, the drying effects of the warming temperatures. But when we do get above normal precipitation, that's when you want to bank it underground. Okay, here's an interesting question for you. I just moved to Michigan. And I can honestly say we factored in climate change. My wife is a climate scientist. I am a climate scientist. We owned a big old house down there in Tucson, not that big, but big enough that it was our retirement savings. It was invested in that house. And we were both worried about the value. We lived through 2008 when the bottom dropped out of the value of that house. And now we're starting to worry, what happens when we hit the shortage in the Rio Grande, in the Colorado River? And all of a sudden, the first state that gets shorted in a shortage is Arizona. People start saying Arizona's not the place to invest in. People stop coming there. It's already warming up so much. The snowbirds are coming, 2 weeks later in the fall, and they're leaving 2 weeks earlier in the spring. Will the bottom drop out of the housing market in Arizona because of climate change? And could that happen soon? I think it could, because once we get a shortage on the Colorado, you watch. We'll all be around for that in the next couple of years. And where is 90% of the fresh water in this country? Go blue. That's University of Michigan's. For the one, I know there's one alumni in the room. There she is. All right. So we have to think, as a country, how are we going to share water? We're not going to be pumping Great Lakes water over here, but we might be pumping it to the high plains. The Southwest, though, where would they get more water? Scratch your head for a while. Think about that. Okay, to conclude, and we'll have time for questions, I hope, because I love these. Usually open a can of worms. Everybody's got some questions, and I like that discussion. The Southwest water is threatened, and we know why, and we know with confidence. We know great confidence. I've said I would bet my house that we're going to get further drying. That's a good bet. Living in Arizona might not be. Warming temperatures and megadrought are key risks. I've explained that. Of course, the climate models, many of them show the storm tracks moving northward in the northern hemisphere and southward in the southern hemisphere. We understand why. As warming occurs, it moves the tracks towards the poles. That's going to affect us too. That's going to dry out in New Mexico and Arizona. We're really in the bullseye of this. But the headwaters might still manage to get by with no big change in precipitation. But they'll still get the temperature impact, which is huge, and I hope I've convinced you of that. Okay? These risks are shared around the world. I like to think if we were to solve this problem of global warming, the Southwest is going to be the place for renewable energy generation, both wind and solar. We'd also be the place that, instead of China, which is obviously positioning themselves to be the go-to place for energy and water solutions around the world, we should be that. New Mexico has a spaceport. That's cool. That's looking to the future. But we really should, in the Southwest, be looking for all of these water-saving strategies and technologies, and being the place everywhere around the world that they go to get the knowledge and get those technologies. That's the future economy for the Southwest, not sticking our head in the drier and drier sand as this problem gets worse. Is there any good news? I said yes earlier, and there are two things that make it good news. There'll be wet years. And in Arizona, where I really got to know a lot of the water managers, I did everything except get down on one knee and beg. From now on, when we get a good year, don't allocate that water to another user. Put it underground. You don't have to build more reservoirs. Put it underground. You get the same yield back. Because if you put it in a reservoir, it's just going to evaporate. Right? If you put it underground, you're going to lose some water to recovery. But that's a great place to bank water. We're doing it in Arizona. They should take every year that's above normal and stick it underground. California's doing that, Nevada's doing that, Arizona's doing it. We're not doing it enough. But the real good news here is that we know what the problem is. The metaphor has been used before. I'll use it again. This is like you've gone to the doctor and you know something's really bad, and it's a cancer. And your first news, the first thought is like, oh shit, I'm gonna die. But then the doctor says, no, not anymore. This is the kind of cancer that we can cure, and you can have a perfectly good quality of life, right? How many of us know someone who's managed to fight cancer now? Because the doctors have figured out how to diagnose it and then use very specific treatments for that cancer to ensure that we have good odds of a good life thereafter, and we won't die from that cancer. This is the same darn thing with climate change. Scientists know what's happening, period. This whole crap about, we're uncertain this, uncertain that. We know why it's warming. We know with great confidence why it's warming. And the fact that our water supply is getting hammered by the warming, we know that really well. So there's not any doubt. So the question is, do we opt for aspirin and treat the symptoms? Or do we nail the cause of what is the Southwest cancer, which is warming? That's our choice. And the beautiful thing about this is we know all of this with really good confidence. And even better, obviously, if we want to switch to renewable energy, the Southwest is in better shape than Saudi Arabia was with oil. We've got the sun, we've got the wind. Of course, Michigan has the water. Thank you.